Oh, are you certified on YouTube?
What's that?
Certified on YouTube.
Certified.
Verified, I guess.
Verified. I don't have enough subscribers to be monetized. So.
No ads.
No, I don't think so. Me and I like 20 subscribers. All right, good morning, everyone. So let's finish off this chapter. So basically, so far we've been saying that, again, we put in a battery, which supplies a constant potential difference. We'll talk more about that in this upcoming chapter, which then creates an electric field inside of the conductor, which then causes the charged particles, which we'll pretend are positively charged particles, to accelerate in the direction of the electric field. But again, these guys are going to make head-on collisions, elastic collisions with all the atoms inside of the wire, which causes it to slow down so it doesn't get accelerated, but ends up moving at constant velocity. So this is our picture of what resistance and currents and all that good stuff is. So basically, we want to justify this picture a little bit more and talk more about this particular velocity, which is going to be called the drift velocity. So the electrons, which are moving through, act as if they're moving with some sort of constant velocity instead of some sort of constant acceleration. So to do that, we're going to talk about a new quantity called current density, which is given by a J. So by definition, the current density is equal to the actual current divided by the cross-sectional area. So it's the currents per unit area. So currents we know has units of amps. So this is an amp per meter squared. So this is the units of our current density. So first of all, what's the difference between current and current density? So current, we said, was, well, if we took our wire and we simply cut out a cross-sectional area, so let's say this was our area of interest, then the current was simply the number of charges which pass through this particular cross-sectional area in a given number of time. So what I'm doing is I'm basically averaging over the entire wire of all the charges which are passing through. But it doesn't really tell me how the charges are moving through the wire in a location-to-location way. So basically meaning it doesn't tell me how many charges are moving through the center, how many are moving on the outside, or anywhere in between. This is the job of the current density. So what the current density is it's actually a vectorial quantity. So in all intents and purposes, this guy is actually a vector, which points in the direction of the electric field. So what the current density then is it's basically typically a position-dependent quantity, which tells me what the actual flow of the charges look like inside of the wire itself. And then the current is then the average over the current densities. So basically all that means is if I have my wire like this, it might turn out that I have a lot of charged particles moving through the center of the wire. And then as I move towards the outside of the wire, the amount of charges I have start to decrease until eventually I get to the outside of the wire, and then I have, say, no particles moving through at all. So this could be one possible way to get charged particles moving through. Or I could have the opposite. I could basically have no charged particles moving through the center, and then as I move towards the outside, I gain more and more and more charged particles moving through. So this would be then my current density. So the current density basically tells me is how are the charged particles moving through this particular wire in a position-dependent formation. So basically meaning, do I have more going through the center? Do I have more going through the outside? Is it constant everywhere through? What does this thing actually tell me? And then the current from here, since this guy's a vector, in general, this is actually going to be equal to the integral of the current density dotted by the differential area, where this differential area is the cross-sectional area. Now, don't worry too much about that definition. I just basically want to say that, again, the current then is the average over all of these current densities. So this is what the current actually is. So the current is an average over the entirety of the wire itself, talking about how the currents on average, or how the particles are on average moving through my wire. But the current density talks specifically about how it is changing from location to location to location. So it turns out then as we're going to see here in a second, the current density ends up being directly proportional to the drift velocity, which means that the current itself is also directly proportional to the drift velocity. So let's see that. So let's actually talk about that. So first things first, let's say I have my wire. So here's my wire. And let's say that the electrons are moving through, or my charged particles, positive Q here, are moving through the wire with an average drift velocity of 8. So let's say at the initial amount of time, my charged particle is here. And then at some later time, say delta t, my charged particle has now moved to here. But I'm imagining that I have a whole stream of charged particles, and let's assume for now that our current density is simply equal to a constant. So all the particles are moving the same everywhere throughout here. So in this amount of time t, what happens then is that this charged particle has moved this distance of L. So L in this case then is going to be the drift velocity simply multiplied by the time delta t. But since my wire has a cross-sectional area of A, what happens then is what's really happening is I have a whole collection of charged particles sweeping out this particular volume here. So in this case, the volume which is swept out then is going to be equal to the cross-sectional area times the length at which these charged particles have traveled in this amount of time of delta t. Which means then that this is going to be equal to the cross-sectional area times the drift velocity times the change in time delta t. So this is my volume. So we can then say the amount of charge which is contained inside of that volume is then equal to our change in charge, which is then equal to the number of charges I have times then the charge of each one of those charges. Right? So here what I have are electrons moving or protons moving, and each one of those has exactly the same amount of charge. Now, from here, we can define a new quantity, little n, where little n is then equal to the number of particles divided by the volume. So this is what's known as the charge density. So this thing then has units of what? Per meter cubed. So this is the number of particles per meter cubed. So the charge density basically just means what is the density of the charge carriers do I have inside of my wire. Now this will be dependent on the type of material that my wire is made out of. So for example, if I'm dealing with copper, copper has a different number density or charge density than that of gold, because gold is a better conductor, so it has more available charge carriers that can actually move through. So good. So that means then we can rewrite this then as the charge density times the volume times the total charge Q. By here, the volume, and we already wrote down, is simply equal to the cross-sectional area times the drift velocity times the change in time. So from here, this is then going to be equal to the number density times the charge times the area times the drift velocity times our change in time. From here, we know current is equal to the change in charge divided by the change in time. So that this is the amount of charge which has passed through in this amount of time delta t. Then the amount of current then is simply going to be this amount of charge divided by that time of delta t. It's going to be equal to the number density or the charge density times the charge of the charge carrier times then the cross-sectional area times the drift velocity times the change in time, all divided by the change in time. Well, what's true about those two changes in times? They're the same. They're going to cancel out. Do that. Finally, this thing says then that the current is actually equal to the current density, charge density, sorry, times the charge times the cross-sectional area times then the drift velocity. This goes back to our claim that these guys move with an average velocity of the drift velocity, which we said basically earlier that you can think of the current as the average velocity at which these charged particles move. So this is the relationship between these now that we talked about the current density, we know the current density then is equal to the current divided by the cross-sectional area. So now if I take this guy and divide by the cross-sectional area, that cross-sectional area will change. So this is that this is the charge density times the charge of the charge carrier times the direct velocity. So this is my current density. Or written as a vector, this guy then is equal to the charge times the charge density times the direct velocity written as a vector. So this is our vectorial quantity. So okay, the current density is directly related to the direct velocity, and then the current is also directly related to the direct velocity. So again, as we said earlier when we started all this, you can think of the fact that the current is basically how fast the charged particles are moving through our wire, which is what this thing actually says. So this current then is directly proportional to the drift velocity, just multiplied by some number. Okay.
What is that unit on charge density?
The unit on charge density is 1 over meter cubed. Yeah. So number of particles, we just say it's a number of particles that doesn't have a unit to it. So another way you can think about this is particles per meter cubed. So if you want to think about it that way, those would be particles per meter cubed. So units wise, it's just per meter cubed. Okay. So this is our current density. So having said that, let's do an example. I'm going to go over this stuff before I get in here. So this is, we have a copper wire, which has a 3.2 millimeter in diameter. So that's my wire. Carries a current of 5 amps. Wants us then to determine the current density in the wire and the direct velocity of the free electrons, and then finally estimate the RMS speed of the electrons, assuming that the electrons act as an ideal gas at 20 degrees Celsius. So assume there is 1 electron per copper atom, which is free to glucose. Oh, good. So let's talk about this. So here it wants the current density. So if we want the current density, we now know that the current density is simply equal to the current divided by the cross-sectional area. Here, we're given the current. The current is simply 5 amps. We know the radius, so we also know the cross-sectional area. So in this case, our current density then is going to be equal to the current divided by the cross-sectional area of a circle, which will be our first question on the upcoming exam, since somebody knew what that was. No, okay. So plug all this in. So this then becomes what? 5 amps divided by pi times 3.2 millimeters, which I put into meters, so it's 10 to the minus cube. Squared. Did I get my numbers? What I find in this case then is?
That's the diameter. Does that matter? Not the,
Was it the diameter?
yeah.
Thank you. So the diameter, so this works out to be the 6.2 times 10 to the 5th amps per meter squared. So this is my current density. So it also wants me then, in part B, to find the drift velocity. So how fast are these electrons moving through our copper wire here? So we now know that what the current density is related to the drift velocity by the charge density times the charge of our charge carriers, which in this case are electrons. So these have a charge of the fundamental charge times then the drift velocity. So from here, this then says that the drift velocity is equal to the current density divided by the charge density times the charge of an electron. So here, since we're dealing with copper, all we then have to do is look up what is the number density for copper. So either charge density or number density, either one of those get you in the right place. So look at our numbers, what we get in this case then is this works out to be 0.05 millimeters per second. So ultimately what it says is under a current of 5 amps, on average, these particles are moving at 0.05 millimeters per second. How fast is that? Ridiculously slow. So now, let's take a part Z. So part Z then says, now estimate the RMS speed of the electrons, assuming they behave like an ideal gas. Okay. So let's go back to part C. So hopefully, you remember from 175 that the RMS velocity is equal to the square root of 3 times the Boltzmann's constant times the temperature divided by the mass. If you don't remember that, don't worry about it. We're not going to use it again, but that's great. So it just says that in some sort of ideal gas, the average RMS velocity at which the particles are moving are related to its temperature this way. So here, Boltzmann's constant is just a number. The temperature has to be in Celsius, which it is actually has to be in Kelvin. So to know this temperature is actually Kelvin, so it should be 273.15 plus 20 degrees, which means that this is 293.15. And then the mass here is the mass of the electron. So the mass of the electron is 9.11 times 10 to the minus 31 kilograms. Look at our numbers. What we find in this case then is that this works out to be about 1.2 times 10 to the 5th meters per second. So, what's the point of this problem? So the point of this problem is basically to point out the fact that what? The wires inside of the electrons inside of the wire. So this is my wire here. What's happening is that they have an RMS velocity of 1.2 times 10 to the 5th meters per second, which means that if I was looking at the electrons, each one of these guys is flying around in some sort of random direction at a ridiculously fast rate of 1.2 times 10 to the 5th meters per second. But what happens then is when we apply our potential difference to then create the electric field to cause the electrons to slowly move down, what happens then is even though these guys are zooming around in different directions, this section here is then slowly propagating down the wire or slowly migrating down the wire at a ridiculously slow rate of 0.05 meters or millimeters per second. So even though these guys are zipping around in every different direction with an RMS velocity given this way, when I apply that potential difference to apply that electric field, what happens then is even though they're still zipping around, they're going to slowly migrate down the wire. So imagine them kind of blocking off this section here. It's going to slowly migrate down the wire at a rate of 0.05 millimeters per second. So this is kind of our mental picture of what's happening. So these electrons are flying around in all kinds of different directions, but they're going to slowly propagate down the wire due to the presence of this electric field. This is what's actually physically happening. So let me ask you this question. Since the electrons inside of the wire are moving at 0.05 millimeters per second, and this is my light switch here, so if I turn this guy off, and then I turn it back on, of course now you're not going to turn it. All right. That's the opposite of always what I want to do. So when I turn it back on, the lights came on almost instantaneously. Right? But let's say there's, I don't know, like a meter between this location and this location here. So if you think about, if I had an electron which was sitting here, and then I turn on my lights, how long is it going to take for that single electron to go from here to a meter away? It's going to take hours, right? It's going to take like 5 hours for that single electron to go from the light switch all the way to the lights themselves. So why is it when I turn on the lights turn on almost instantaneously, even though it takes like 5 hours for that electron there to move all the way through into the light bulb? Why is this the case?
Does it have to do with the volume, since that was the larger?
Part of the volume, but something has to do with volumes. That's right. So think about the number density. So how many electrons are inside of that wire? Close to an infinite number, right? So even though this single electron that's sitting here takes 5 hours to go all the way to that light bulb, but is that the only electron that exists inside of my system? So I also have electrons that are basically sitting just about ready to fall into that light bulb. So as soon as I turn on my switch, those electrons start falling in, which then causes the light to come on instantaneous because this thing is filled with, again, electrons scattered everywhere through the wire, which are moving on average with a velocity of 1.2 times 10 to the 5th meters per second in all possible different directions. So okay, even though the electrons themselves are propagating down the wire at a very slow rate, but we have to remember that this entire wire is filled with electrons, basically an infinite amount of electrons, which means that as soon as I turn on that switch, even though they're migrating at a 0.05 millimeters per second, there's so many of them that they're going to go through rather rapidly and through that light bulb, giving us light. Okay? So this is drift velocity. So one more thing to talk about. It turns out that using current density, we can actually rewrite Ohm's law. So let's revisit Ohm's law. So good. So what does Ohm's law say? So again, Ohm's law says that the potential is equal to the current times the resistance. So let's draw a picture again. So here's my wire. Here's my potential source. So what's happening here is, again, I'm setting up a potential difference across this guy, which is equal to the potential difference across the battery. So whatever the battery is here, across my resistor, in this case, the potential difference is the same. My resistor here has a length L to it, and it also has a cross-sectional area, which means that the resistance of our resistor is the resistivity times the length divided by the cross-sectional area. But I can also rewrite the potential in terms of the electric field, because now I have an electric field which is pointing in this direction. Remembering the fact that the magnitude of the electric field is equal to the change in potential, which in this case is simply equal to the potential difference across here, divided by the length of the wire. Which means in this case then, that the potential difference is equal to simply the electric field times the length of the wire. So, we also know now that the current is simply equal to the current density divided by the cross-sectional area. So let's use all these things and put them in here. So what this says then is I can rewrite the left-hand side as simply the electric field times the length of the wire. The right-hand side then becomes the current density divided by the cross-sectional area. I'm sorry. That's backwards. Current density is current divided by area, which means so that's current density times the area, times the resistance, which is simply equal to the resistivity times the length of the wire divided by the cross-sectional So this area here cancels this area. This length here cancels this length. So what this says then is that the electric field is actually equal to the resistivity times the current density. But also remembering that the resistivity is equal to 1 over the conductivity, I can multiply that over to here, or actually divide, so this thing finally becomes the current density is equal to the conductivity times the electric field. But since the electric field is a vector, and the current density is also a vector, I can write it this way. So this is actually Ohm's law, or what we're going to call in this class the microscopic version of Ohm's law. So when we started all this, what we said is we have this current density which points in exactly the same direction as the electric field, which we see from here, because the conductivity is always a positive quantity. So since this guy is positive, these two have to point in exactly the same direction. So this says that the current density points in the same direction as the electric field. It's just multiplied by the conductivity. So this is actually Ohm's law.
Is sigma still the Q over A in this way?
No, so this is the conductivity, not the surface charge density. Good question. So this is conductivity. So conductivity has units of 1 over ohm meters. So that's units of conductivity. So it's not the surface charge density, just to confuse you as much as possible.
How would we?
Mostly by
given
units.
volume?
Mostly by units, because again, what you're thinking of as that one, that is the surface charge density. So that sigma is equal to Q divided by A, which then has units of coulombs per meter squared. But this one has units of 1 over ohm meters, so it has different units. So units would be the first way to go to determine which one is which. And a lot of times it also just depends on the context of what's happening.
I just feel like, is it something that you would give us?
Yeah, or I make you solve for it. So for example, I would tell you J and I would tell you E and I would ask what's the conductivity. Or I would tell you the resistivity and then you can find the conductivity from doing the inverse of that. Or I would just flat out tell you the conductivity.
Is it typically like a constant?
It's a constant depending on the type of material. That's right. So again, copper has a different conductivity than gold. Gold would have a greater conductivity than that of copper. Okay. So using these, let's do a couple more examples. And I did not write down the numbers for these, so hopefully somebody has calculators and can calculate the numbers for these guys. So let's do this. So this one says that we have 115 volts is applied across a wire that is 10 meters long and has a 0.3 millimeter radius. The magnitude of the current density is 0.14 times 10 to the 4th amps per meter squared. And from this, it wants us to find the resistivity of the wire. Okay. So basically, all we're using here now is this version of Ohm's law, which is the same thing. It just has a resistivity instead of the conductivity. It's basically the only difference. So from here, we can then say that the electric field is equal to the resistivity times the current density. Now, what we know here is the current density. We're told that in the problem. The electric field, we're not told directly, but we are told the potential and we're told the length, which is basically all we need. Because from here, again, the potential is equal to the electric field times the length, which means the electric field is from here, the potential divided by the length. So for this guy, I'm just going to rewrite this then as the potential divided by the length is then equal to the resistivity times the current density. From here, if I want to solve for the resistivity, my resistivity then is just equal to the potential difference divided by the current density times the length. So let's plug in our other numbers. So this becomes 115 divided by 1.4 times 10 to the 4th times the length, which is 10 meters. And somebody has a calculator. I wasn't smart enough to write this solution. 2 times 10 to the negative.
8.2 times 10
Oh.
to the negative
8.2 times 10 to the
Double check that for you.
negative 4.
Yeah.
And then it says units of ohm meters. This is my resistance. Not too bad.
I'm confused how the density is on the
How the current density, because I'm solving for this guy, so I'm just dividing this over here. It's okay. Let's do one more. So next one says, near Earth, the density of protons in solar winds, which is the stream of particles from the sun, is, so this is our number density or our charge density, 8.7 per centimeter cubed. So I have 8.7 protons per centimeter cubed. And their speed is about 470 kilometers per second. We'll talk about what solar winds are and all that good stuff in a second. So then it wants us to find the current density of these protons. And then from there, if the Earth's magnetic field did not deflect the protons, we'll talk about that also in a second, what total current would Earth receive? So let's talk about these things. Let's draw a pretty picture. So here's my Earth, and somewhere out here is the sun. So what are solar winds? So basically what happens is the sun has a magnetic field. That magnetic field sometimes will puncture out through the surface of the sun and then make what are called promenades. So basically what happens is I get a big section of magnetic field which blows out from the sun itself, and then charged particles are being strewn through here back into the sun here. So what happens then is if the promenade gets too big, eventually it breaks. What happens in that case then is if it gets too big, this thing breaks, and then when it breaks, it then shoots all those charged particles which are going through the inside of this promenade, shoots it out in every possible different direction away from the sun. This is what we call solar winds. So basically these guys break, and when they break, in this case they're carrying a bunch of protons, and then these protons are going to hurl themselves towards the Earth with this drift velocity. So in this case, the 470 kilometers per second would be then the drift velocity of these charged particles as they move towards the Earth. So what happens then is the Earth is being constantly bombarded with all of these charged particles, which means that if we didn't have a magnetic field, what happened then is that all of these charged particles would just rip through the Earth and basically scorch the Earth. We'll talk about how much current we're going to have across the Earth here in a second. So basically, there would be so much current going across the surface of the Earth that the Earth would basically be on fire, and there would be no way that any of us would exist without the magnetic field. So what our Earth's magnetic field actually does is we have a magnetic field. So here's our magnetic field. So what happens is these charged particles actually get caught up inside of the Earth's magnetic field, or some of them actually pull off and cause the magnetic field to do something more like this. But basically, the magnetic field of the Earth actually shields us from these charged particles, which we'll talk more about later. But basically, these charged particles get caught up in the Earth's magnetic field. Some will drag the magnetic field basically off in this direction, but it shields the Earth so that most of these charged particles don't actually make it through to the surface of the Earth. So from here, we want to know for part A, what is the current density of these protons? Good. So part A, and we know current density is related to the drift velocity, the charge density times the charge of the charge carrier, which in this case is a proton, which means that this is, again, is the fundamental charge. Here, we're told that this is 8.7 times 10, or sorry, 8.7 per meter cubed or centimeter cubed. So first thing we're going to have to do is actually convert this to per meter cubed. And then go from there. So let's do that. So first things first, note that what? How many centimeters are in a meter?
Isn't it times 1,000 divided by 3,600? That's what I use.
Well, 3,600 would be when we're doing seconds, typically. So
Per second.
meters. Oh, this one. So good job on?
Yeah.
So this is kilometers, so this is 470,000 meters per second. Which one?
Times 8 times 1,000.
Okay. So we know there are 10 centimeters in 1 meter, which means if I cube both sides, then I have 10 to the third centimeters cubed is equal to 1 meter cubed. I'm sorry? Oh yeah, there's 100, not 10. One of those days. Okay. Good. Thank you, Jeff. Something didn't look right. There we go. So this is equal to what? 1 times 10 to the 2 raised to the third power times centimeter cubed is equal to 1 meter cubed, which means I have 1 times 10 to the 6 centimeters cubed and 1 meter. So this is how many I have in this direction. Good. So in this case, we're told that the number density then is 8.7 per centimeter cubed, which I then have to turn into per meter cubed, which means that what? So let's invert everything. So this means 1 over meters cubed is then equal to 1 over 1 times 10 to the 6th centimeters cubed. Which means that 1 over centimeters cubed is going to be the same thing then as 1 times 10 to the 6th per meter cubed divided by per centimeter cubed. So in this case, the per meter or per centimeter cubes are going to cancel, which will be this in per meter cubed. Times the charge in the fundamental charge, which is 1.602 times 10 to the minus 19 coulombs times the drift velocity, which in this case is 470,000 meters per second. Who's got a calculator? Multiply all those things. I forgot to bring that.
It's just 8.7 times 10 to the 6, is that right?
And then this is amps per meter squared. Anybody else multiply it out? Is that what they got?
No, I was asking, that was my question for the,
Oh yeah, so that's 8.7 times 10 to the 6th is that first one. Yes.
my answer is 6.55 times 10 to the negative 7. That's what I got.
6.55 times 10 minus 7. Gotcha. Sorry. I misunderstood.
For when you're converting to the centimeters cubed to meters cubed, shouldn't that be to the -6?
Well, no. So let's go back to what we had. So we had, it was what? 1 times 10 to the 6th centimeters cubed is equal to 1 meter cubed. Right, so when I take a 1 over, so this is 1 times 10 to the minus 6th, 1 over centimeters cubed is then equal to 1 over meters cubed. But then I have to bring it back to the other side because I have 1 over centimeters cubed that I want to put into 1 meter cubed. Does that make sense?
Yeah.
Okay. So you go. Okay. So this is our current density. So then it says, okay, so if the Earth's magnetic field did not deflect the protons, what is then the total current that the Earth would feel? So we know that the current then would be equal to simply the current density times the cross-sectional area. So in this case, the charged particles are going through, which means that they don't see the surface area of the Earth. What they really see is only the cross-sectional area of the Earth. So as it's coming through, what it sees is that this thing looks effectively like a circle. So not the surface area, but actually just the cross-sectional area. So this is then going to be equal to that number times then pi times the radius of the Earth squared. So this guy then is going to be equal to 6.55 times 10 to the minus 7 times pi times the radius of the Earth. Is, so this is 6.37 times 10 to the 6th meters squared. Millions times 6, right? Yeah. So, who wants to multiply that?
Got 8.35 times 77. That's not exactly.
8.35 times 10 to the 7th amps. So that means that if the Earth's magnetic field did not exist, we would have a constant current basically across the surface of the Earth, which would be about 8.35 times 10 to the 7th amps. And noting that a person dies if they have a current of 100 amps. So basically this would scorch the entire surface of the Earth, and then nothing would grow, nothing would live. Earth would be poor and barren, and we wouldn't actually exist, so we'd never have the conversation. So this is current density. Okay? So that brings us to today's group assignments. So let's talk about today's group assignments. So this says that we have a okay, so we have a potential difference of 1.2 volts is to be applied to a 33 meter long 18 gauge copper wire. So whenever you hear gauges of wires, all it means is it's talking about the cross-sectional area of the wire. So it's opposite of what you'd usually think. The higher the gauge, the smaller the cross-sectional area. The smaller the gauge, the bigger the cross-sectional area. So in this case, all it means then is that the gauge is 0.04 inches. So this is the diameter of the wire. So from here, I want you to calculate the current, the magnitude of the charge density, the drift velocity of the electrons, the magnitude of the electric field within inside of the wire, and the rate at which thermal energy will appear in the wire. So remember, rate of energy is just power. So what is the power which is being lost inside of this wire? That's all this is talking about. So useful things you need to know are the resistivity of copper, which is 1.72 times 10 to the minus 8 ohm meters, and the number density or the charge density of copper is 8.47 times 10 to the 22 per centimeter cubed. So, these are difference, a length, and a diameter. And we know the voltage, 1.2 volts.
Resistors.
It's so small. Enlarge it.
It won't let me make it bigger.
What is the length of
33 meters. That's good.
We know the resistivity.
How's that? All better.
Yeah.
Lose the numbers on
That's
the bottom.
much better.
Well,
Yes.
well, let me do a slideshow.
How much do we store? What were the numbers of
Bottom ones. You have resistivity is 1.72 times 10 minus 8.
3 zeros, by the way.
And number density or charge density is 8.47 times 10 to the
Yeah.
2. But note the units are
Take it by
per
2.58.
meter or centimeter cube, not meter cube. So meter per.
I was like, inches to meters. That's.
I
I don't really want to do that.
We solve for the resistivity, knowing the density of copper and the length
Okay, so far.
over the area. And then we can plug it into this equation and solve for I for the current, because we know the potential
Oh,
difference.
Right.
You know what I mean?
I know what you mean.
So it's just pi r squared. That.
Is the area? And don't forget to change your inches into meters.
I let people do that one.
Yes. That's what Google's there for. Today's Thursday, isn't it? We have one. Oh, it looks really weird.
No, I'm just solving for R. I would equal B times B over.
Mine was off my mind.
Magnitude. Got the first one.
Okay, first one. Just using Ohm's law.
Yes, solve for R.
Good, 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 good. Okay, so far?
When it says magnitude of the current density, isn't it just solving for current density? Because that's J plus I over the area again.
I think so.
So we have
So that's 4 times 20 divided by the cross-sectional area is that's what we look. And so then we get it about 0.7. Calculation. That's why it was.
to get this one, we solve for I here, so just I over the area. Is the E just the charge of the electron?
Yeah.
Because in that case, we would use the.
It's just the
We would use the VG.
What should we put in meters? It's in centimeters.
Within the middle triangle here, that 1.06 times 10 to the negative 19.
Or sometimes 10 to 20. Centimeters times 100, centimeters cubed to meters cubed is times 10 to the 6. So you just add 6 to it. Exactly.
It was the same one.
Yeah, I think so. For D. So it's just J equals I over A. Okay. So we just found I. So it's 1.7 divided by the cross-sectional area.
Did you get 1.56? That's not what I got when I multiplied it.
Because it is the 1.7 times 10 to the 2 times the 1.6. And then it's the 2.11 divided by that.
I'm getting that plug in. 2.11 times divided by 8.47 times 10 to the 28.
Just make sure you get these stuff, because otherwise it'll just divide the very first time when you try to multiply it. So try one and do one. So when I multiply the first two. Times the 100. I use pretty good. And maybe because you're wrong. Your answer.
No, I think we have it flipped. Well, I have it flipped. I have it as this over that. That's why I wrote it that way.
That's still right. So K equals NQ dD. And so the 2.11 times that dD. So this gets divided by this. The only thing is I use my memory for the 2.11. So I'm trying to just multiply. So just do this part. Just multiply. See what happens.
That's, yeah, so power delivered. Is equal to power loss.
Good.
Do I have my exponents? Correct.
Negative 19. Yeah.
-10 to the 6. You didn't get that one multiplied by that, did you? No, like when you just multiply the bottom two together.
Right. It's a 1.35. I don't think that matters.
What was that?
That's the question.
I just still keep getting 2.35 and it looks like everything's set up right. I don't know what to do.
2.35.
Getting that every time. Do you see anything wrong?
Per meter cubed.
Should I put the 2 in there? Usually do the 2. I think it makes a difference.
Maybe parentheses. I don't know. I have to take a look at it. But
Which is weird, because she's typing the same thing, we're getting into much. Like the 8.47 times 10 to the 28 times the 1.602. I'm getting one answer, like we're typing in the exact same way, I'm getting one answer, she's getting different. If I, like, what my calculator is putting out is, gets me to the answer that's up there.
Right.
But I don't know what hers is.
Both of them.
their calculators don't like you doing.
Nerd.
Yes, ma'am.
Do you want the numbers?
No. What is it, 8.47?
Yeah, times 10 to the 28.
Make sure that doesn't happen on the test.
Hang on. No, not log.
I mean, I knew how to get to it. I know you don't take off points if like the math is wrong.
28. Okay, good. And then find
Fundamental
602.
charge.
And
1.602.
where's your minus one?
I have 1.06. We're all dyslexic.
Wait, for real?
Yes. I put 1.06.
Oh, yeah, you did.
1.62.
Yeah, you did. That's your problem.
1.602.
I even looked at it and I was like, this is the same. It's not the same.
I feel like I do that so much. I'm like,
And then what's the numerator that I'm dividing that by?
2.1.
should get it now.
2.11 times 10 to the 6. Which,
What a waste of time.
that might give you a little off, because I used my memory and got the exact answer, but I don't know how.
So
I just had the wrong
got
number, fundamental charge.
1.55502 times 10 to the minus 4.
Close enough.
It's just
1.56. Yes.
1.56.
Thank you.
You're welcome.
We solved that. You already did D.
Yeah,
Just
it's
the
just,
potential because the electric tunneling.
just the potential.
Okay, go ahead. I'm not being able to use a calculator. Okay.
Just not plugging in the right number. I don't know how to use the calculator.
There. That's okay. I can't.
Thermal energy. So the answer is in a lot, so and then asking for power.
That's what I was gonna ask. Yeah. It's current times potential.
So it's power loss, right? It's how much will you're in the wire.
Alright.
2.6.
All right, looks like everybody was successful with that. Fantastic. So, in our last 10 minutes that we have for today, we're going to go ahead and start the next chapter. So, next chapter basically wants us to take all the things that we now know, things like potential sources, currents, resistors, capacitors, all that good stuff, and start putting all them into circuits. So basically all we're going to do in this chapter is basically look at circuits. So first thing to talk about is what's known as an electromotive force. So an electromotive force is anything which supplies a constant potential difference, or at least not necessarily constant, but at least supplies a potential source. So don't let the word force kind of fool you here. It's actually not a force, it's a potential. So here, the electromotive force, which we're going to call squiggly E here, is actually just a potential source. So same as units of volts, not units of force. So again, it's anything which supplies some sort of potential source. So it could be a battery, it could be a generator, it could be anything that supplies a constant potential source. So as we talked about when we talk about batteries, what happens is in an ideal battery, the potential difference stays constant, which means that whether I have a current running through my battery or not, the amount of potential which is supplied by the battery remains simply fixed. It's simply a constant. But in a realistic battery, that's not the case. So to talk about that, we're going to talk about what's called a terminal voltage. So you guys already looked at this in the lab. I'll just talk about it actually formally. So a terminal voltage means is if I have 2 points that I'm measuring the potential across, say A and B, what happens then is with an ideal battery or a real battery, as long as I'm not running any potential source across it, then the terminal voltage across these particular points is simply equal to that of the EMF. So whatever is supplying the actual potential. So as long as I have no currents running through either an ideal or a real battery, then the potential difference across the terminals, or our terminal voltage here, is simply equal to that of the EMF. Okay, so whatever is actually supplying the potential. However, if I took my ideal battery, and I run current through it, so now I have a current, say, flowing in this direction, and I take my realistic battery, and I do the same thing, and I run current through it, so I have this thing closed in some sort of circuit, so current is running through my system. Turns out here, with a realistic battery, the terminal voltage across these two is still equal to that of simply the EMF, but for a realistic battery, the terminal voltage across the battery itself is less than that of the EMF. So what happens is in a realistic battery, the potential that you have across the battery is going to deplete as you start running current through it. Now, when we talked about batteries, we talked about the reason for that. Again, if I was looking at the acid-based battery, I'm dissolving one of the, in this case, anode, and the cathode, I'm just stripping off charges from it, but it takes a long time for this to actually happen. So that's happening at a constant rate. So when I actually pull current through the system, I'm pulling energy through the system, which means that overall, the rate at which that's happening can't keep up with the draw at which it is that I'm taking the potential or causing the electrons to move through the circuit, which means that the potential difference actually ends up dropping. So the way we typically then model a realistic battery versus that of an ideal battery is we say in an idealized battery, we simply have our EMF source. So in this case, this would be our battery with positive terminal and negative terminal, where this thing simply has an EMF. That's it. For a realistic battery, what we say is that, well, we have an ideal battery on the inside. So this is my EMF, but we're going to couple that to a resistor. So on the inside of an ideal, or sorry, realistic battery, we have a little tiny internal resistance, which we're going to call little r. So as the current then starts to run through the battery, what happens in this case then is this is going to become equal to the EMF minus the current which is being drawn through, times then the value of this internal resistance. Okay? So what we imagine then as a real battery is actually an EMF attached in series with a resistor. So we can never get around this resistor since it's always connected in series with the battery. So as soon as I start drawing current through the system, my then EMF stays the same, but my terminal velocity decreases by the amount of that current which is running through it. Now, again, the EMF supplies a constant potential, but it doesn't dictate the current. What actually dictates the current is the resistance. So my resistance dictates the current, while the purpose of the EMF is simply to create this constant potential. So what we're going to be doing is we're going to be taking circuits, we're going to be connecting batteries to a whole bunch of different resistors. Right? So what's the point of actually doing that? So we kind of talked about in the lab, what happens is I can either decrease the overall resistance of a circuit or decrease the overall resistance of a circuit depending on how I actually connect my resistors together. So why do we do that? Well, we do that because from a manufacturing point of view, it doesn't make sense to make any possible resistor that somebody's going to use at some point in their life. Because if I was making resistors, if somebody needed, say, a 1.1 ohm resistor and somebody needed a 1.11 ohm resistor, I would have to manufacture each one of those different ones. So any slight difference in resistance, I would have to manufacture a different resistor to have that particular amount of resistance, which means that I would have to effectively construct an infinite amount of different resistors. And then hope somebody's going to buy it at some point. So what we do instead is we only make certain resistors which have certain resistances, and then allow people to create their own resistances by connecting resistors together in either what we call series or parallel. So this is the reason that we actually connect these guys in series and parallel. So let's talk about how we actually do this. So what we want to do is start connecting resistors in series and parallel. And then we're going to do the same thing with capacitors. So let's look at resistors first. So as we saw in lab, if I connect these guys in series, that means that these guys are connected directly to each other. There is no possible way for the current to go in any other direction. So if I have R1 here, R2 here, R3 here, these guys are in series because the current is forced to go through each one of these different resistors. So this is what we call series. Parallel, there are now options. So I could instead have R1 here, R2 here, R3 here, and then connect these guys back to the battery. So these are what are called parallel, because now there are junctions or nodes. So this one here are what we call junctions or nodes, which are points where the current has its choice to go into different types of directions. So here, I could run currents, and the current might decide to go through R1 and go around back into the battery. Well, that's one option, so it's going to be one current, I1. Or the current might want to go through R2 and go down in this direction, back to the battery. So that would have a separate current of I2. And then I can also have it run through and go through R3. In that case, it would have its different currents of I3. Now, which one it decides to go through is typically going to be dictated by the amount of resistance. The more resistance there is, the less amount of current I'm going to have go through, as opposed to the less amount of resistance, I would have a lot more current going through. So if you think about these guys being hoses, so if I had a faucet here, and then I had a bunch of hoses connected to it, so that it was going through one central hose and then spread off into 3 different hoses, the water is going to go through the hose which has the larger cross-sectional area. The bigger cross-sectional area will allow a lot more water to go through than something which has a small cross-sectional area, which means I'd have a lot less water going through. Or, for those of you who want to be a doctor at some point, you can think about also with the hearts and your veins and your blood vessels. So in that case, when your heart is pumping, the blood is going to go through the veins and the arteries, which have the bigger cross-sectional area, as opposed to ones which have a smaller cross-sectional area, which means you wouldn't have as much blood coming through. So this is one of the big problems with blood clots or cholesterol. It reduces the size of the arteries and the veins, causing less blood to go through, especially if it goes to the brain, then that's going to cause a big problem. So we can use the same kind of philosophy in those situations as well. So again, this is a series. These guys are connected directly to each other. And these guys are what we call parallel. Now, our claim is that we're going to be able to collapse either one of these two down to what's known as an equivalent resistor. So basically, what's going to happen is I'm going to have a battery connected to simply one resistor, which is what we call the equivalent resistance. So the claim here is that these 3 connected in series acts as if they're a single resistor, where these 3 here, which are in parallel, also act as a separate resistor. So our job then is to determine what is the equivalent resistance when I have these guys in series, and what is my equivalent resistance when I have these guys in parallel. And I'm out of time, so I'm going to have to put you in suspense. Even though we've already seen this in lab, but that's okay. Drive it. So, great. So after we do that, we'll do a couple examples, and then we'll do capacitors and the same thing, and then we'll talk about what happens if we have more than one battery. See everybody in about 45 minutes, or start playing with magnetic fields today.